Good morning, students. Since most of y'all have joined with the session, I think we can start today's lecture now. Can y'all see my screen?
Yes, madam.
Yes, madam.
Okay, right. So we were talking about linear models. And if you can remember, we were talking about the simple linear model. That is when you have one X variable and one response variable, how to fix your regression model, right? So we discuss how to find the slope and intercept with the given data set. And when you fix the linear model, in order to check the accuracy of the linear model, we know we have some assumptions to check, right? That your errors are normally distributed, they are having a zero mean, and they are having a constant variance. So based on all these assumptions, we have fitted the linear model. And also we discussed that after fitting the linear model, there are some properties that we can see in the simple linear regression models. So we are going to talk about some more properties today. So last week also we discussed this. Now when you fit your regression model, we know how to calculate the residuals, right? Residuals means now when you fit the linear model, we know we get an equation. So when you get your equation, by substituting your x values to the equation, you can find the predicted or the forecasted y values, right? So we call them as y hat values. So when you take the difference between the original response variable, original values of your response variable, or in other words, original y values and your y hat values, that will give you the error, right? So this error we call as the residual. And then if you take the summation of all these residuals in any fitted model for any data set, you will see the summation will add up to 0, right? And also if you take the mean value of the original response variable and also the y hat values, again you will see you get the same value for the original mean of the original response variable and also for the y hat values. So this is here you can see in point 2, when you take the mean value of the original response variable, so you have to take the summation of all the y values and divide by the number of observations. If you want to take the mean value of the y hat values, you have to take the summation and divide by the observation. So you will see you get the same value for if you calculate these two mean values. And also the least square line always passes through the centroid point, centroid of the data. That is, if you find x bar and y bar, and if you check with the fitted line, you will see this x bar, y bar coordinate, it's passing through the fitted line, right? So I will just share you, let's check these 3 points using the data set that we used to discuss in last week, that we used to discuss the other properties. Right, so this is the example that we discussed in last week, right? So if you can remember, we were discussing about a data set where x was the training time and y was the hours that were taken by a particular employee to complete a given task. So we fitted a regression line. So, and we calculated I hat values also. And here, if you can remember when we calculated the residual, so error terms, right? Here I consider all the decimal places and consider calculated the error terms. And you can see, if you look at this value, this is the summation of all these error terms. You can see it's equal to 10 to power minus 5. That is, the summation is very close to 0. So you can see when you take the summation of these residuals, it's adding up to 0, right? So the other point, the point number 2 that I explained, if you take the mean value of the y variable, so you can see this is your y variable. So if you take the summation of y values, that is 150.5. So the mean value of y variable is, what you have to do is, that is y bar we have already calculated, 150.5 divided by 8, since you have 8 observations. Now let me check this mean value of y hat values. So this is our y hat values. So let's take the summation of all these values. So I'm going to take the summation of y hat values. You can see summation is again 150.5. So if you want to take the mean of the yi hat values, that is 150.5, you have to divide by 8. You can see you get the same mean value, right? This is the mean of yi hat, and this is the mean of original response variable. So that is exactly the same. And if you look at, if you check whether the centroid point passes through the given line, so we can see this is our fitted line, right? This is our beta 1 value minus 0.456, and this is our beta naught value 27.64. So if you check this centroid points, we know we have already calculated our x bar value was 19.375 and y bar was 18.8125. So if these two centroid points passing through the fitted line, that is, if you substitute the two centroid points, it should satisfy the the equation of the fitted regression model. So equation is this. So let's check. I'm going to calculate the I'm going to substitute the x bar value to the equation. So our equation beta naught value is this plus our beta 1 value is this, and I'm going to substitute the x bar value to the equation. So you can see it's 18.8125. So that is the exact value of y bar. So that what happened was, when we substitute the x bar value for the given equation, when you substitute the x bar for, this is the equation, we substitute x bar value for x, then we got the value of y bar. That is x bar and y bar coordinate. It satisfies the fitted equation. That is, it's passing through this fitted line, right? So you can see all these three properties. It satisfies the fitted regression model. It's satisfying all these three properties. So not only for this data set, for any given data set, you can see all these properties when you fitted a simple linear regression model. And with that, so actually we can prove all these properties. So you can easily prove that the summation is the summation of the residuals adding up to 0, and you can prove the two mean values of the responses and the predicted values are equal, and also you can prove that this one we actually I gave you last week. So you can see this the proof of these two I have given you as assignment 2. If you just check the cal, I have already uploaded assignment 2 also. So I hope you all know tomorrow, because of the strike, you will not be having any academic activities. So because of that, you have to take your 1.5 hour time of lecture, and then you can complete this assignment 2, and you have to submit that before Friday. But if you feel like you don't have time, submitting assignment 2 is not necessary, but you can submit, right? To get evaluate yourself, you can submit, and we'll be discussing assignment 1 and 2 both on Friday at the lecture, right? So, but from assignment 1, since you all have submitted it on time, I saw 52 of you all have submitted, so I'll be taking marks from assignment 1. From assignment 2, no marks will be calculated, but you can submit that to get an evaluation by yourself, right? Okay, so now in this case, now if you when you have your data set, if you want to get now we know when you have one response variable and one independent variable, now we know how to fit the simple linear regression model, how to find the slope and how to find the intercept. At the same time, if you want to find an estimate for the population variance of your data set, you can use this equation, right? We know the population variance is denoted by sigma. So if you're interested about finding an estimate for the population variance, so you can use this equation, and this one also we can easily prove, right? So we'll be discussing this proof on Friday, but you can give a try by yourself. Okay. And then what we are going to do is like after fitting the regression model, you can use the assumptions to check the accuracy. At the same time, we can conduct some hypothesis testings in order to evaluate our fitted model, right? So for that, we use some of the important results. Now, that is if you look at this one. Now, this is the fitted regression model when you have one response variable and when you have one x variable, right? You can see yi is equal to beta naught plus beta 1 xi plus epsilon I. So our assumptions are, we know these, the residual terms, they are normally distributed with zero mean and constant variance. Now in this case, we can see this beta 1 and beta naught and beta 1, they are linear functions of yi. And residuals are normally distributed, right? So if the residuals are normally distributed, and if you can see that the beta naught and beta 1 are linear functions, we know, then we can conclude that beta 1 and beta naught are also normally distributed, as they are the linear functions of this yi. So in that case, actually we can show, if you check the mean value of beta 1, you will see that is equal to beta 1, mean value of beta 1 hat, that is equal to beta 1. And if you check the variance of the beta 1 hat, you will see that is equal to sigma squared divided by SXX. So we know what is this SXX, that is the squared summation of xi minus x bar, right? So we can easily show, if you just check the mean value of beta 1 hat is equal to beta 1, and the variance of beta 1 hat is equal to sigma square divided by SXX, right? So with the use of this, now we can convert this estimate into a standard normal distribution. So we know how to convert any given value to a standard normal distribution. You have to subtract the mean and divide by the standard deviation. අපි ඕනෙම value එකක් standard normal කරන්නේ අදාළ variable එකෙන් අපි ආගේ mean එක අඩු කරලා standard deviation එකෙන් බෙදුවා. So same thing we are going to do here. You can see now our variable is beta 1 hat. So we take beta 1 hat, and since the mean value is equal to beta 1, I'm going to subtract beta 1. So beta 1 hat minus beta 1. And now I have to divide this by the standard deviation. Since the variance is sigma squared divided by SXX, so you have to take the square root value to get the standard deviation. So what happens? Now we have converted this term into the standard normal distribution. So that is normally distributed with zero mean and variance of 1. Right, so in this case, you can see the sigma value, sigma squared is the population variance value. But sometimes for some data sets, we don't know the value of the population variance. So in such cases, we can use this estimator to estimate the population variance. You can see this is sigma squared hat. So this, if you substitute the values to this equation using the data set, that will give you an estimate for your population variance. So if the population variance is unknown, right, in this case also you can substitute the estimator of the estimated value of the population variance. So the same equation you can replace by sigma square hat, right? Okay, so the same equation we can replace by sigma square hat, right? So since we replace the population variance by the estimated value, now this test statistic is having a t distribution with degrees of freedom n minus 2. Right, so if you know the population variance, then you can take this distribution as having a standard normal distribution. But if we have no idea about the population variance, what we can do is we take this sigma value, sigma squared value, the population variance, and we are going to replace that using the estimated value, right? And then we can come up with the t distribution, right? So if you just further solve it by substituting this equation for sigma squared hat, you can see, you can further simplify this one as per the equation below, right? This is the final equation. When you have no idea about the population variance, you can use this equation, which is having this test statistic, which is having a t distribution to make inferences about our model, right? Let me discuss how to make these inferences later, but this is how we construct the two test statistics. In this case, the proof of this, how we get the mean value as equal to beta 1, how we get the variance as equal to sigma squared divided by SXX, that is not necessary for you. But if you just follow and if you just read the reference books, you will see the proof as well. But those things are not I'm not going to question those things in the examination, right? Okay, so now with the same manner, now we know, I told you now beta 1 hat and beta naught hat both are having a normal distributions, right? So with this, using the same procedure, we can come up with this is the test statistic for the beta 1, and we can come up with this test statistic for beta naught as well. So this is the test statistic for beta naught, which is having again t distribution, because you can see here we have replaced our sigma square value with the estimator, right? Same thing. The only difference is the numerator. Here we have beta naught hat minus beta naught, and here we have beta 1 hat minus beta 1, and here the standard deviation is sigma squared hat divided by SXX. Here the standard deviation is sigma squared hat summation xi squared divided by nxx, right? So the standard deviation is different because we know when you take the model, if you find out the variance would be different for beta naught and beta 1, right? Anyway, now we can use these two test statistics to make inferences about our fitted model. Right, so one of the inference that we can make is when we are interested about constructing confidence interval for beta 1 and for beta naught, we can use this test statistics, right? Now imagine you know the population variance. In that case, if you want to construct a 95% confidence interval for beta 1, right? So we know what is 95% confidence interval, right? So we give two values, right? We give two bands and we are 95% confident that our the value of our parameter would fall within these two values, right? So that is the meaning of the 95% confidence interval, but I'm not going to explain you like I'm not going to explain you in detail because in inference course you I think you have done 95% confidence intervals and you're confident with that, right? So here, if you want to calculate a 95% confidence interval for beta 1, now if the population variance is known, we know we can come up with the first test statistic, right? This one, that is beta 1 hat minus beta 1 divided by square root of sigma squared divided by sxx. So this is having a standard normal distribution. So when we calculate the 95% confidence interval, what happens? We take this test statistic and we assume this test statistic is in between the two table values, right? So same thing you have to do here. The table values would be minus 1.96 and plus 1.96, since we are interested about 95% confidence interval and since this is coming from the standard normal distribution, right? So since we are calculating the confidence interval for beta 1, then what you have to do, you have to keep only beta 1, right, in the middle of the two inequalities, and then you have to put the other terms into two sides of the inequalities to get the confidence interval. So you will see then you have beta 1 hat minus 1.96. This is the way standard deviation term, and beta 1 hat plus 1.96 times the standard deviation term. So this one we can use when you want to construct a 95% confidence interval for beta 1 for your slope parameter, in other words, and also when the population variance is known. And imagine you have no idea about the population variance. So we discuss when you have no idea about the population variance, we can replace this sigma squared with the estimated value. So that is sigma squared hat. So in that case, if you replace this by sigma squared hat, what will happen? The distribution will converge to a t distribution, not a standard normal. So the t distribution, you have to take the table values from the t distribution. So these are the table values of the t distribution, and then you can again construct a 95% confidence interval for beta 1. So that would be beta 1 hat minus t in minus 2.5%, and this is the standard deviation term, and the beta 1 hat plus the table value into standard deviation term. So this you can use to construct a 95% confidence interval for beta 1 when the population variance is unknown. Right, same procedure you can use to construct a 95% confidence interval for beta naught when the population variance is known and the population variance is unknown. So you can see when the population variance is known, we can use the table value 1.96 and here the standard deviation times standard deviation 4 plus the estimator, right? So you have This one, this is the 95% confidence interval for beta naught. And if you have no idea about the population variance, when the population variance is unknown, you can replace this sigma squared value by sigma squared hat. And then in that case, you will get the t distribution. So you have to take the values from the t distribution. Now, if you wonder whether you have to remember all these equations for the examination, yes, you have to, but you don't have to by heart, because all these confidence intervals you can construct easily if you just remember the two test statistics, right? If you just remember these two test statistics. Now, for an example, if you just remember this one, beta 1 hat minus beta 1 divided by sigma squares over sxx, the square root of this term, you have to only remember that. So when you only remember this, what you have to do is, when you are constructing a confidence interval for beta 1, since you are using the standard normal table, you have to take, if it is 95% confidence interval, we know the table values are minus 1.96 and plus 1.96. So you have to multiply the two table values from the standard deviation, right? And then you have to keep only beta 1 in the middle, because we are constructing the confidence interval for beta 1. So then you can, the two sides you can multiply by minus 1, and then you can, again what you have to do is, you can remove beta 1 hat term from the two sides by adding beta 1 hat to the equation. So then you will get the confidence interval, right? So then when you use the t distribution, you have to just replace the population variance by the estimated value, right? So that's what you have to do. You have to remember, but not, you don't have to by heart, just get the logic and remember that, right? So why we are so interested about these test statistics, right? And why we are interested about these confidence intervals. So when we fitted our regression model, we can conduct some hypothesis testings to make sure that our model is the best fit, right, to our data set. Now, in that case, now after fitting our model, we can check whether the fitted value of our intercept, that is beta naught, is true or correct, true or false, right? So in that case, you can see we can just undergo of this hypothesis. You can see, that is, we can check whether the beta naught value is equal to 0 or beta naught value is not equal to 0. So when you do conduct this hypothesis testing, so if we come up with the conclusion that our beta naught value is equal to 0, that is, there is no point of using our estimated value with the regression model. අපි මේ ටෙස් hypothesis testing එක කරනකොට හදිස්සියවත් අපේ conclusion එක beta naught equal 0 කියන එක නම් අපිට ඇත්තටම අපේ model එකෙන් අපි හොයාගත්ත beta naught ගෙන් අපිට වැඩක් නැහැ. Right? So we can't use that for the predictions, for the forecasting purposes. So that's why we check using our data set the accuracy of the model parameters using these hypothesis testings. Okay. So in that case, what we do is, if you want to test for the beta naught, so our null hypothesis is beta naught equal to 0, and our alternative hypothesis is beta naught not equal to 0. And we are using this test statistic, the same test statistic which we use to construct the confidence interval. And what we do is, we take the test statistic and we substitute our data set. And you can see here we have taken the test statistic when the population variance is unknown. So it's having a t distribution. So we substitute all the values to the test statistic, and then we check we check the table values. So since this is coming from the t distribution, the two table values would be minus tn minus 2, 2.5%, and the same, the positive term of the same value, since the t distribution is a symmetric one. So you have to check the test statistic value, and if the test statistic value falls in between these two table values, then we are not going to reject our null hypothesis, right? That is, we can conclude beta naught is equal to 0. But if we can reject our null hypothesis, that is, in other terms, if our table value exceed or if it is less than the test statistic is less than or exceed the given table values, then we can conclude that beta naught is not equal to 0. So in that case, we can confirm the calculated intercept value is correct. So our we have evidence to confirm that the regression line uh, this is regression line is having an intercept value, right? So that is how we conduct the test for the hypothesis for beta naught. With the same process, you can conduct a test for beta 1 as well. Okay, so that is, in that case, our H naught would be beta 1 equal to 0, H1 would be beta 1 not equal to 0, and we are using the test statistic for beta, which we developed for beta 1. And again, we have to substitute the value for the test statistic and check with the table values. If the test statistic is in between the two table values, we do not reject. And if it is exceeding or less than the table values, we can reject and conclude that beta 1 is not equal to 0. That is, we can be sure about the slope value of the fitted regression line. Right, so in this case, actually now you can see in this both hypotheses, we tested whether beta naught and beta 1 values, they are equal to 0. But let's imagine you want to test your fitted beta 1 value is equal to 10, or whether it's equal to 2.5. You want to test whether your beta 1 value is equal to a specific value. In that case, it is also possible. So only difference is when you are writing the hypothesis, you have to write beta 1 equal to the given value that you're going to test. Let's say 2.5. So beta 1 equal to 2.5, beta 1 not equal to 2.5. So I have denoted that by using beta 1 asterisk. So in that case, when you take the test statistic, now, in the previous one, we have the test statistic. If you look at the numerator, we have beta 1 hat only. But actually, that is beta 1 hat minus 0, since we are testing beta 1 equal to 0 versus beta 1 not equal to 0. In this case, since we are testing beta 1 hat asterisk term, so you can take beta 1 hat minus beta 1 asterisk. You can take the difference between these two values, since here the difference between beta 1 hat minus 0 is again equal to beta 1 hat. So here you have, since you have a specific value, you have to take the difference. That is the only change you have to do, and all the other terms are the same. So you have to just substitute and check with the table values to get your decision. And also, since we know now, when the inference course we discuss, when you take the this test statistic, right? That is, when you take this estimated value of the population variance, divide by the population variance into n minus 2. This is having a chi-square distribution with degrees of freedom n minus 2. So based on this chi-square distribution, we can construct a confidence interval for sigma squared as well. So this is the confidence interval for sigma squared based on the chi-square distribution. right? So by substituting values, we can find a 95% confidence interval for population variance as well. So these are the equations, how to find the confidence intervals and how to undergo with the hypothesis testings. So we'll go through with an example, then you will understand how to use this equations practically. So before that, do you have any questions? Okay, then let's look at the example. So you can see following data were obtained from an experiment carried out to determine the relationship between temperature and the yield of chemical process. Okay, so you have to fit a suitable model to forecast yield of the chemical process. So you have two variables. So this chemical process, they have conducted using different temperatures, and they have recorded the yield. So we have to check the relationship between the temperature and the yield. And we have to construct a model to forecast the yield. So if you want to forecast the yield, we know that is our response variable. So your response variable is y, and it's depending on the temperature value. So your x variable is the temperature. So that is the first thing to identify when you are provided with the data set. What is your x variable and what is your y variable? All right, so they're asking us to fit a suitable model to forecast the yield. And then we have to estimate the yield of the chemical process when the temperature is 45 Celsius, right? When the temperature is equal to 45 Celsius, we have to forecast, or we have to predict what is the yield value, what is the expected yield value. And then in C, they ask you to carry out a suitable hypothesis test to determine whether the regression coefficients of the model are equal to 0 or not. So since this is the simple linear regression, we know we have two parameters. That is, we can get two estimates for beta naught and beta 1. So we can check whether beta naught is equal to 0 and beta 1 is equal to 0 using our hypothesis testing. And then we have to obtain a 95% confidence interval for beta 1. Okay, so let's see how to do this example. Okay, so right, so I hope you can see my data set. Can you see the Excel sheet now?
Yes, ma'am.
Right. So you can see I just put all the values to this Excel sheet. So we have our temperature values. We have 8 observations. That is our X variable, and we have our yield value. So that is what we are going to predict. That is our Y variable. There also we have 8 values. So what is the first thing? First thing is we have to find the fitted regression model. So that is, we have to find beta naught and beta 1 first of all, right? So what you have to do is, first, if you want to calculate beta naught and beta 1, first we have to calculate x bar and y bar. So what I have done here is, here I have taken the summation of all these x values, that is 216. So to calculate x bar, you have to take 216 divide by 8, since you have 8 observations. And then if you take the summation of these all y values, that is 91.3. So if you want to calculate the mean of the y, you have to take 91.3, you have to divide it by 8. So we can have x bar and y bar values. And then what you have to do is, if you take the equation of beta 1 and beta naught, so we have to take the difference between I and x bar and y and y bar. So here what you have to do is, here I have subtract x bar value, right? That is 27 from each and every observation of x. And then in this column, column E, what I have done is I have taken the difference between every y value with its mean, that is 11.41. So I get yi minus y bar. Then we multiply the two values, that is xi minus x bar into yi minus y bar. And here in column G, I have xi minus x bar squared value, right? That is here we have xi minus x bar value, and I have taken the square term here, right? So in the first case, that is all we want to find out the fitted regression line, right? In that case, if you want to find the fitted regression line, so this is the equation of beta 1 hat, right? So what you have to do is, if you want to find the fitted regression equation in the beta 1 hat, you can see the numerator is the summation of xi minus x bar into yi minus y bar. That is the summation of this product, the column F, that is this value, that you have to divide by a summation of xi minus x bar squared value. So xi minus x bar squared summation is this. So then you will have beta 1 hat value. This is your slope. And then to calculate the beta naught value, if you look at the equation, you have y bar. So y bar value is 11.4125 minus, you have to take beta 1 hat value multiplied by x bar. X bar is 27. So when you substitute, you get beta naught. So this is our equation. So in other words, you can write your equation as y equal, the beta naught value is minus 13.4821 plus 0.922 into x. So this is our fitted model using the data set. So that is the first thing they are asking us to do, right? We have to fit the regression model using our data set. So last week also we discussed how to fit the regression model for a given data set. So same procedure you have to apply here to fit the regression model. Is that clear? Any
Yes,
questions regarding the model fitting? Okay, so then in part 2, in part B, they are asking you to find out the yield when the temperature is equal to 45. So if this is your regression line, if you want to forecast the yield when temperature is equal to 45, that is, temperature is the x value. So when x is equal to 45, we have to find the corresponding y value. In other words, we have to substitute 45 for x and find out the corresponding y value. So what I'm going to do is, so I'm going to find the yi hat value when x equal to yi hat value when x equal to 45, right? So this is equal to the model equation, beta naught value is this plus beta 1 value is 0.922 into, now our x value is 45. So when you substitute 45 for x, you will get the corresponding yield value. In that case, that is 28.00893. So this is the corresponding yield value when your temperature is equal to 45, right? So we are done with that. So actually here I just calculated the y hat values also, just to show you that when you take the summation of the residuals, it's adding up to 0. In this case is also, you can see here the summation of the residuals, it's very close to 0. So you can see for any given data set, all those properties, we can show that all those properties are satisfied, right? Okay. And then now we have completed task 1 and task 2. We fitted the regression model. We forecasted the yield for a given x value. And then now we have to check with the model whether our model parameters are equal to 0 or not. So first we can start with, let's say, we can start with beta 1. So if you want to start with beta 1, so when we start with beta 1, we can first, the hypothesis we can write down whether beta 1 is equal to 0 and beta 1 is not equal to 0. The hypothesis first you have to write it down. So I write the hypothesis first. So first you can write down the hypothesis, that is right, beta 1 equal to 0 and h naught is beta 1 equal to 0, h1 is beta 1 not equal to 0. So based on the model, fitted model, we are going to find out whether the slope value is equal to 0 or not. Now in this case, you can see we are given with just the data set. We have no idea about the population variance. So we have to go with the t distribution, right? So this is the test statistic in the t distribution that we have to use, right? So that is beta 1 hat minus beta 1 divided by sigma square hat over sxx. We have to take this test statistic, which is having a t distribution with degrees of freedom in -2, in order to conclude our decision. Now in this case, since we are interested about beta 1 equal to 0, beta 1 not equal to 0, so when you look at the numerator, when you calculate the test statistic, beta 1 you can substitute as 0, since that is what we are testing. So if you calculate the test statistic in this case, okay, the first task is to calculate the test statistic, capital T. And now that is test statistic is equal to beta 1 hat. So beta 1 hat value is this one, 0.922. And that one you have to divide by sigma square hat over sxx. Right? So in this case, you have to now calculate the sigma square hat. Okay? And sxx value we already have calculated, that is x I minus x bar squared summation, that is 168. That value we know. So now what we have to calculate is sigma squared hat. So I just copy and paste the equation, then that will be clear for you. Yeah. So this is the equation that we can use to calculate the sigma square hat. So you can see when you calculate the sigma square hat, let's calculate the sigma square hat. First you have 1 over n minus 2. So since we have 8 observations, 1 over n minus 2 would be 1 over 8 minus 2, that is 1 over 6. That we have to multiply by, first one is SYY. SYY value means yi minus y bar squared squared summation. So yi minus y bar squared we have calculated, and if you take the summation of that column, that would be 166.6288. So that we can substitute, right? Minus, then we have to calculate Sxy squared. So Sxy is xi minus x bar into yi minus y bar, this value, and we have to take the squared term of that. So I'm going to take the squared value of this, and that one we have to divide by Sxx, that is xi minus x bar squared value. So that is 162, and then the whole thing that you have to multiply from this 1 over 6 value. So I have to put another bracket. So you will see, you will get the estimated value for the population variance as 3.96. So we just substituted the values using the data set for this equation. 1 over n is 8, s y is yi minus y bar squared summation, that is 166.6288 minus sxy squared means sxy is 154.9. So we have to take the square term there, divide by sxx, that is sxx is 168. So when you substitute and simplify, you will get sigma squared hat is equal to 3.9678. So now we can find out the test statistic, right? Let's substitute for the test statistic. T is equal to beta 1 hat. So beta 1 hat is this, minus beta 1 is 0. Now we are testing for 0. So for the numerator, we don't have to substitute any other term. This one you have to divide by the square root of sigma squared hat. So this is sigma squared hat, the estimated value, right? Divide by, you can see the sigma squared hat, you have to divide by sxx. So sxx value is this. That will give you the test statistics. So our test statistic value is this, based on the data set, that is 5.760879. Now to take the decision, right? To take the decision, what you have to do is we have to check whether this test statistic is in between the two table values. Now, if you check the degrees of freedom, which is equal to n minus 2. In this case, we have n is 8, 8 minus 2. The degrees of freedom is in this case 6, right? And we are looking for 95% confidence intervals. So let's check the table value. So first we have to check the t table now, since we are using the t-test statistic. Let me share the t-table with you. Share the t-table. Right, I think you can see the t-table now. Can you all see it?
Yes, madam.
Yes.
Okay, right. So the degrees of freedom that we are interested is 6. So from the first column, we have to read 6. Okay. And since we are interested about 95% confidence interval, so our alpha value is 0.05. And since we are interested about two values from the either side of the distribution, so we have to divide alpha by 2, that is 0.025, right? So if you just look at for the two tail values with alpha 0.02 with alpha 0.05, you can see in this case, this is the column that you have to check, because in this column, if you look at this notation, it says T 0.975, and that is the cumulative probability. So the cumulative probability means up to that point, the area of the distribution is equal to 0.975. So that is from that point to plus infinity, you have 0.05 area. So this is the value that we are interested about from the t table. So you have to read that value. So in that case, that is you can see that is 2.447. So we know, you can see in the t table, you can read only the positive values, because t distribution is a symmetric distribution. If you find one value, the value of the other side is exactly same as that value, but only the difference is the sign. So this is the positive value. So the value which is on your left hand side, you can take it as the same value with the negative mark. So from the table, you have to first read the degrees of freedom as 6. And since the alpha value is equal to 0.05, and since it's two tail one, because we are interested about two values from either side of the distribution, alpha is 0.05, because our confidence interval is 95. So if our confidence interval is 99%, you have to go with alpha 0.01. Right here, alpha is 0.05. Why? Our confidence interval is 95. Then when you read these two values at the intersection point, you get the corresponding table value, that is 2.447. Right? So let me get back to the calculation. Okay, so in this case, now we found out T from the T distribution, n minus 1 is 6, and here the alpha divided by alpha value is 0.25, right? And in this case, 0.025. So the corresponding value from the table was 2.447. So the same value you can take. So this is the Tn minus 2, 2.5% value from the table. So same value you can take with the minus mark to get the value of the other side. Right? So that is, we can just since I put a minus value here, right? Anyway, I'll take this as This is the negative value of this one, to take the table value of the other side. So that would, you can just take it as just as the negative value of this, that is minus 2.447. Now we have to check whether the estimated value is in between these two table values. Now you can see the test statistic value is 5.76. That is actually greater than 2.44. That is not in between these two values. So what you can do is, if it is in between these two values, we cannot reject, but you can see this exceeds one value of this exceeds 2.447, one table value. That is, we can conclude we have enough evidence to reject H naught. So our decision is we reject H naught, right? So if we are going to reject H naught, that is, we reject beta 1 is equal to 0. Okay, so in other words, we can just conclude that beta 1 is not equal to 0. H naught for reject කරනවා කියන්නේ අපි beta 1 equal 0 කියන එක reject කරනවා. අපිට කියන්න පුළුවන් beta 1 0 නෙමෙයි. That is, in other words, what we have fitted, what we have estimated for the slope is true, right? It's accurate because there exists a value for beta 1. අපි data set එක පාවිච්චි කරලා beta 1ට මේ හොයාගත්ත value එක true කියන එක අපිට decide කරන්න පුළුවන් මේ hypothesis testing එකෙන්. So the same thing we can do in order to test beta naught as well. So the first thing that you have to do is, first you have to write down your hypothesis, right? That is H naught is beta naught equal to 0 and H1 is beta naught not equal to 0. So first you can write down the hypothesis. Right, that is beta naught equal to 0 versus beta 1 not equal to 0. So let's calculate the test statistic for beta naught. So you can see this is the test statistic when you use the beta naught. So let's calculate the test statistic there. So what you have to do is, if you look at the numerator, you have beta naught hat minus beta naught. But since we are testing whether beta naught is equal to 0 here, you don't have to substitute 0. So that is, when you substitute 0, your numerator will become beta naught hat. So that is, in the test statistic, your numerator is beta naught hat. So the beta naught hat is this one. That we have to divide by the square root of, let's see. Here we have to divide this by the square root of sigma squared hat into summation of the xi squared terms divided by n sxx. So in this case, actually, we have to calculate this summation of the xi values. So in this column, if I just take xi squared values. So let me take xi squared values here. We have not calculated the xi squared values. So in order to calculate the xi squared values, we have to take the original x value and take its squared term. So like this, you can calculate the xi squared values. Right, so after calculating the xi squared values, we can take the summation of this column. So let's take the summation of this column. Right, so summation is 6,000. So in that case, now we can calculate the test statistic for beta naught. So here in the numerator, we have beta naught hat that we have to divide by square root value of sigma squared hat. So the sigma squared value also we calculated. So that one I'm going to put here and multiply by summation of the xi squared values. That also we calculated. And then we have to divide that thing by n. N is 8 into sxx. Sxx value is xi minus x bar squared summation, this one, and then can take the test statistic value. So you can see the test statistic value is minus 3.20, right? Here the test statistic was 5.76, and the test statistic is coming from the same t distribution. So since the degrees of freedom are the same and it's coming from the same distribution, right, we can use the same table values to get the decision of this hypothesis. So you can see, if you look at the table values, we found out it's 2.44 and minus 2.44. And if you check with the test statistic, we can see it's the test statistic is less than minus 2.447. That is, our test statistic is not in between the two table values. So in that case, we can come to the conclusion that we have enough evidence to reject H naught. So in this case also, we reject H naught. So if you reject H naught, that is, we are rejecting that beta naught is equal to 0. So in other words, we can conclude that beta naught is not equal to 0. So what we have fitted using our model is true. There exists an intercept. So we can conclude that the value that we have received for intercept is true. Okay, so this is how you do the hypothesis testings using your data set to test whether your beta 1 and beta naught values are true and correct. Okay, so then as the last part, they ask you to calculate a 95% confidence interval for beta 1. So in this case, so when you calculate the 95% confidence interval for beta 1, we can use this 95% confidence interval since we have no idea about the population variance. So actually we have found all these terms. We have to just substitute. But here I will just find out the value of sigma squared hat divided by sxx square root, right? In that case, I will just show you how to do that. So what we have to do is we have to take the square root value of sigma squared hat, square root value of the sigma squared hat. So we calculated the sigma squared hat and we have to just substitute this one and then divide by sxx. So this is the xxx value, right? So then we can just find it. So here we get the value for square root of sigma squared hat divided by sxx. Now we can find out the confidence interval. So I will find first the lower limit, right? So the lower limit, to find the lower limit, what you have to do is lower limit is beta 1 hat. So the beta 1 is equal to this value, right? Beta 1 minus, now the table value we have to take 2.447, and that you have to multiply by this value, that is sigma squared hat over sxx square root. So when you will get the lower limit value. And then we can find the upper limit value as well by substituting the values for the equation. So the upper limit value you can find, again we have beta 1 hat. So beta 1 is equal to this plus, then we have table value 2.447 into square root of sigma squared hat over sxx, right? So this is the upper limit. So the 95% confidence interval, 95% confidence interval is equal to, our lower limit is 0.546 and our upper limit is 1.298. So this is the confidence, 95% confidence interval based on our data set. That is, we are 95% sure that our is the parameter, the true parameter of beta 1 would fall in between 0.54 and 1.298. Right? So this is how we construct the confidence interval. So I hope you're clear with, when you are given with the data set, how to fit the model and how to check the accuracy of the models using the appropriate hypothesis testings, and also how to construct the confidence interval. Up to that point, do you have any questions? Crystal clear? All right, so then right, so right. So from this is where we stopped. So we discussed this example. So if you look at the note, you can see for the assignment 2, there is another proof which comes under the next section. But I have already uploaded assignment 2. So don't worry. I think I will stop from this point because since we discussed too much of calculations today, I think that's enough for today, right? Because I can't even see y'all, so I don't know whether y'all understood or not. So anyway, you can practice. You can practice the calculations we discussed as well. So we'll discuss from prediction in the next lecture, but yeah, you can give a try to complete assignment number 2, and you can upload it if you want to evaluate yourself. And if you have any questions, you can ask. If not, we can wrap up the session. Do you all understand what I'm telling you all? Did you understand what we discussed today?
Yes, ma'am.
Yes, madam.
Okay, right. Okay, then we'll end the session for today. So tomorrow you have no lectures due to the strike, and on Friday you have lectures at 6 a.m. and we'll be discussing about the assignment on Friday. Okay, thank you for joining with the lecture. Have a nice day.
Thank you, ma'am.